Hello and welcome to my presentation. I'm Stefanie Kaiser from the Technical University in Dortmund in Germany, and my presentation will be about the integration of superstructure optimization under uncertainty and optimal experimental design in early stage process development. The early phase of process design largely determines the final investment and production costs. So one has to take the final design decisions before enough knowledge about the process is generated. So then this process design is based on limited knowledge and uncertain data. If one wants to use process optimization in the design phase, one first has to perform experiments and set up the model equations. Then the process is optimized before it can be built. So this approach is sequential and takes a lot of time. Our goal here is to reduce the effort of knowledge generation and thereby lower the costs for process development and reduce the time to market. To identify the optimal process in an early design phase, the superstructure optimization under uncertainties that was developed by Jochen Steimel and Professor Engell can be used. In superstructure optimization, first a set of process alternatives is generated and the models for the process units are set up. We can then determine the optimal configuration by solving the following optimization problem. It's a two-stage optimization. So in total, we want to minimize the production costs. And the cost function consists of two parts. The first part are the costs taking the first stage decision into account. And these decisions cannot be adapted to the realization of the uncertainties. So they are fixed in the first stage. And these decisions are, for example, either binary decisions, as if a process unit is used or not, or they can also be discrete or continuous decisions, such as the number of stages in a distillation column or the volume of a reactor. The second part of the cost function are the expected costs of the second stage. And in the second stage, operational parameters are optimized that are assumed to be adapted. So they are used as recurse variables. And we use a discrete number of scenarios, which is called capital omega here. We compute and optimize the costs for each scenario and then take the expected costs of the weighted scenarios in the objective function. This optimization problem is solved subject to the physical relations, so the process model. We further have the process specifications and equipment limits as inequality constraints, and usually binary and continuous decisions are involved, so we have to solve an MI-NLP. Usually we have non-convex problems, so we have to use global optimization techniques. While solving the optimization problem, one gets the cost distribution for the different designs. So here you can see the results of an optimization for the three best designs, and each bar represents the costs that were computed for one scenario. So we get, for example, for 25 different scenarios, 25 bars for each design. One now has the problem that it can happen that one cannot identify the best scenario, design, since it may be dependent on the realization of the uncertainties. So for one realization of the uncertainties, one design can be superior over the others, but for a different realization of the uncertainties, it is not. So one has to further refine the model at the optimal operating point to be able to identify the best design. So the idea in this work is to use the superstructure optimization under uncertainties and directly link it to the experimental works, so that we come from this sequential approach to an integrated approach, where we have a fast feedback from the superstructure optimization to the experiments. So by doing so, it is possible to identify promising process alternatives and operating conditions, and then determine the relevant parameters at these optimal operating conditions. So we want to focus the process modeling. And this is done by a close collaboration between industrial chemistry and process modeling and optimization. So how does this methodology then look like? How can we generate the specific knowledge in the early phase of process design with limited experimental effort? So the center of this work is the superstructure optimization under uncertainty that I described before. For this superstructure optimization, we need a process model, and since we are in the early design phase, it will be an uncertain process model, which is based on usually batch experiments and thermodynamic models. We then select the alternatives, and if we already have found the optimal process, we can stop here, but usually this won't be the case, so we continue and perform an optimal design of experiments to determine the relevant parameters. And as I said before, we want to focus these experiments on the relevant parameters. So we do a sensitivity analysis to identify these parameters. Afterwards, the new design experiments are performed and the parameters are estimated. And then with the updated process model, we again do a superstructure optimization under uncertainty and repeat this cycle until we found the optimal process. To identify the most cost influencing among the uncertain parameters, and sensitivity analysis is used. And here we use a linear regression where we regress the objective value to the uncertain parameters. To make the regression coefficients comparable, we use standardized regression coefficients, where each regression coefficient is multiplied with the standard deviation of the uncertain parameters and divided by the standard deviation of the objective function. As a sampling method, we use the Latin hypercube sampling, where we only have a small number of samples, but still can cover the complete parameter space. So as an example, I showed you here an example for the two-dimensional case, so where we only have two parameters, and both parameters are divided in an equal number of layers, and then one sampling point is set in each column and each layer so that we get an even distribution of the sampling points. The large standardized regression coefficients means that this parameter has a large impact on the objective function. Afterwards, the experiments to determine the uncertain parameters further have to be planned. In this work, we focus on planning of batch experiments to determine the relevant parameters. That's because we want to determine parameters of a kinetic model, so we get the concentration profile over time, which can then be used to identify the kinetic constants. We use a d-optimal design of experiments where the determinant of the variance-covariance matrix is decreased. The formula for this matrix is shown here, where QR is the dynamic sensitivity matrix, which consists of the derivatives of the model output R to the parameters at the different sampling times. And QS is then the dynamic sensitivity matrix of the output S respectively. As I said before, we want to focus the experiments on the relevant parameters. So we rate these optimal design of experiments with the standardized regression coefficients that we computed before. The presented methodology is then applied to a case study, which is the hydroaminomethylation of 1-decene, where a rhodium catalyst is used with a sulfoxanthos ligand. In this case study, a thermomorphic solvent system is used. A thermomorphic solvent system is a system with different solvents, usually a polar and an unpolar solvent. And we get a homogeneous mixture at the reaction temperature. And then at a lower temperature, a miscibility gap forms, so we can separate the polar phase from the non-polar phase. It is used in this case because it enables us to recycle the expensive catalyst, which will dissolve in the polar phase here and can then be separated from the product, which will be in the unpolar phase. And during the reaction, water is formed, and this water is separated by a membrane from the recycle. So here I show you the process alternatives of this process. We have 3 binary decisions. The first one is if 1 or 2 reactors are used. The second one is if 1 or 2 decanters are used. And then the third one is if we use a TMS system, as I described, or if we add the unpolar solvent, the dodecane, after the reaction. So then we would have a homogeneous mixture in the reaction, only consisting of the reactants and the polar solvent methanol. And in the decanter, we have a pure extraction. So the first step was to model the process, and our process model consists of 3 parts. The first part is the kinetic model, which is modeled using the Arrhenius approach, and the parameters are fitted to experimental data. The reaction, or the structure of the consists of 2 parts. We have the hydroformulation as the first part, so we use the structure of the kinetic model for this one. And the second part is the reductive amination, so we use the structure of the reductive amination to model this part and combine those 2. The second part of the process model is the thermodynamic model. We have to model both the gas solubilities in the reactor, and we have to model a liquid-liquid equilibrium in the decanter. The gas solubilities are approximated with the gas solubilities in the pure solvent, and they are computed with PC-Saft. PC-Saft is an accurate equation of state, but it has the disadvantage that it's computationally too expensive to be used in optimization. Therefore, my former colleague, Ms. Nentwich, has developed a scheme to fit a neural network, or fit the thermodynamic data by neural networks. So we have surrogate models that compute the same gas solubilities as PC-Saft, but are computationally less expensive and hence can be used in process optimization. The liquid-liquid equilibrium is modeled with the GE model UNIFAC-DO. The last part of the process model is the membrane model, which is modeled by constant retentions for each component. The retentions are defined by 1 minus the rate fraction in the permeate divided by the rate fraction in the feed. We also assume that the specific permeate flow is constant. In the superstructure optimization, only kinetic parameters are considered as uncertain. So these are the pre-exponential factors in the Arrhenius approach and the activation energy. Since we have 9 reactions in total, we get 18 uncertain parameters. We did this 2-stage optimization with 25 different discrete scenarios. So in this diagram, you can see the costs in euro per kilogram of product for the 3 best designs that were identified. And it is possible to see that design 1 is always superior to the others. Design 1 is the design where 2 reactors are used, 2 decanters, and the unpolar solvent dodecane is fed after the reaction. So here, for each scenario, which is represented by 1 bar, one can see that the costs for the design are lower for design 1 than for all other designs. Still, the distribution of the costs is quite large. It differs between approximately 16 and 31. Moreover, one cannot take a decision about the continuous design decisions, for example, the volume of the reaction. Therefore, we want to further refine the process model. In the second stage of the optimization, the operating conditions are adjusted depending on the realization of the uncertainties. So here I show the scaled recurse variables. And one can see that most of these recurse variables are adjusted over the complete range of the variables. So for example, the reaction temperature is adjusted somewhere between the lower and the upper bound of the possible reaction temperature. Afterwards, the standardized regression coefficients were computed for the best design. So they are computed only for the design alternative that is optimal and also for the optimal operating conditions. So here one can see that K3 has the largest impact on the production costs. And this is due to the fact that the reaction 3 only describes the side reaction, so the hydrogenation here. The product of this reaction is only formed in a really small amount, and therefore the parameter cannot be estimated well. So the confidence interval of this parameter is very large, and this then has a high impact on the standardized regression coefficient. This parameter should be determined better in new experiments, and these experiments were then designed using optimal design of experiments with the sampling times, the temperature, the pressure, the catalyst concentration, the gas composition, and the solvent composition as decision variables in the optimization. Here I showed you the result of the designed experiments, and one can see that a low CO2H2 ratio is chosen. So hereby the reaction that was determined as uncertain or as relevant in the sensitivity analysis can be identified better. Taking experiments with the small CO2H2 ratio into account, the confidence interval of this parameter could already be reduced by 30%. Using the new parameters in the superstructure optimization, it was possible to refine the cost distribution of the best design. To sum up this presentation, we contributed to a systematic methodology for early phase process design by combination of superstructure optimization under uncertainty, sensitivity analysis, and optimal design of experiments. Thereby, it is possible to focus the experimental work on determining the most cost-influencing parameter and hence reduce the time for process development. In the future, we want to further refine the model at the optimal operating conditions to get a better model and thereby identify the optimal process. We also want to apply this approach to uncertainties of other process units, for example, the membrane model. We also want to use variance-based methods for global sensitivity analysis instead of the standardized regression coefficients to better identify the cost-relevant parameters. Herewith, I'm already at the end of my presentation, and I would like to thank you for your attention.